So far we have discussed the origin of refraction. It goes back to this wave nature of light and the fact that the frequency of or the velocity of the phase velocity of the light changes as it enters a medium. We defined what the refractive index was, we all have seen that in some form before, and we delved a little deeper into trying to understand why refraction occurs and why light should bend, and consequently why you see different changes in direction when you go from a denser medium to a rarer medium and so on. I will just backtrack a little bit so that we have some continuity and then we can take up a discussion of birefringence from here. So, here is what we were discussing. On the micro scale, remember we mentioned that there are typically two waves that are going on. One is the incident wave, of course, which is your incoming light wave, and the moment it enters a medium typically has atoms which have electrons, naively speaking, and the electric field that accompanies a travelling light wave excites these electrons, they oscillate, and since they are oscillating charges they emit light of their own, and the final light that actually is propagating is the sum of these two. And so we said that to understand why light should bend, we have to look at the total interface wave, the total wave past the interface, pardon me, and that is what we did. We went back to this Maxwell's equation. The equations themselves, you do not need to remember these equations, but at least from the point of view of understanding where this light bending comes from, we can loosely rationalize it using just two of these Maxwell relations involving the electric field. I also told you that the magnetic field was not particularly important because it does analogous stuff and it is always perpendicular to the incoming electric field. And based on this we did some simple calculations and we found that at the interface you have two conditions. You have this, which is that the component of the electric field parallel to the interface remains unchanged, and the component of the interface component of the field that is perpendicular is altered in the ratio of the epsilon being the permittivity, of course, which is also related to the refractive index. Now consequently the arrow direction changes, as you see in this figure here, and so this is really the origin of this bending of light as you go past an interface. And I think we also briefly mentioned about the fact that you can have bending towards the normal, away from the normal. These are things that we have seen in a class, in a ray optics or a geometric optics class before, perhaps in high school, and all of this can be explained, of course, by just taking the ratio epsilon 2 is to epsilon 1, and then that tells us which way the light ray is going to bend. Okay, so now we understand, sort of summarizing, we understand why refraction should occur and why bending should occur. And incidentally, in the process of discussing this, we also figured out that this change can give you absorption, it can give you different degrees of absorption, it can make materials opaque and so on. These are some of the stuff we also discussed in the context of this bending business. Alright, so then we came out to birefringence, and this is what we will start discussing today. This is where we will sort of continue, and I told you that in a typical material, in a typical let us say a glass or some polymer of some sort, the material is usually isotropic, right, which means it is the same in all directions. So if light is incident in one of these directions that is shown here, this or this or this, it is going to basically react in the same way, right. It is going to see the same structure locally, so it is going to see the same types of atoms and their is going to see the same types of atoms, it is going to see the same type of electrons near the atoms, and so it is going to result in the same types of bending or deflection. Now so that means that the refractive index, of course, is independent of the direction, it is independent of what direction the electric field is in, what direction the propagation is in, and so on, right. So this is isotropy that you see in most materials. Now anisotropy, of course, comes up when you have some specific orientation of these atoms in a crystal, for example. I give you the example of calcite, and now depending on which direction the light is coming in with respect to the orientation of the atoms in the structure, you are going to have different types of responses, right. and so now the direction of the electric field with respect to the specific direction or the specific crystal direction becomes important, and as we will see today that is really where some of these effects come from, and that is where we start our quantification of birefringence in the first place. Alright, so let us take off from here and sort of see and look at the origin of birefringence. Now typically there is a property of many of these anisotropic crystals that distinguishes one particular direction, and this particular direction is often called the optical axis or the optic axis. Okay. And usually what will happen is that the refractive index parallel to the axis is different from that perpendicular to the axis. Okay. And when I say parallel and perpendicular, I am referring to the polarization direction. So, if the light polarization is parallel to the optic axis, you will see a different refractive index, which means that that component of the light will travel at a different speed compared to the component that is perpendicular to the axis, to the optical axis. So, just to be a little bit more precise, let us take two different situations. So, here we have our optical axis like this. I am going to call the optical axis as OA, and in this case, in a different case we have the optical axis like this. So, the material's optical axis is pointing upwards and here it is pointing to the right. Okay. And the material of course is 3 dimensional. So, you can imagine it has a third dimension, it has thickness, it looks like a cube for instance, and we will ignore that for now. And let us assume that we have light coming in like this. Okay. So, this is our direction of propagation, this is a direction of propagation, and we will also make axis. So, this is our z axis, this is let us say x, y comes out like this. Okay. Same axis here, x, z and y. Alright, now I am going to denote the polarization along the, so remember the propagation directions along the x, or the polarization, the vector electric field vector can either be along x or along y or in some intermediate direction. So, it has to be in the xy plane. So, I will draw two components, this is the Ex component and this is the Ey component. Okay. So, everywhere along this ray you have these two guys and they are going like this and blah blah blah. Okay. And the same thing is coming here, you have Ex, Ey and it is going like this. Okay. At every point there is an oscillating electric field. It could be this is the component along x, this is the component along y, in general it is along some direction in the xy plane. So, you can resolve it along these two axes and those are the values you get. Okay. In the first case the optical axis is in the direction of propagation. So, if the polarization is parallel to OA, or if the electric field vector is what I am referring to as polarization, if the electric field vector is parallel to OA, then the refractive index is let us see NE, it is just a nomenclature, subscript E refers to extraordinary, but does not matter for now, it is just a different value, and if E bar is perpendicular to OA, then the refractive index is NO. O stands for ordinary, but again we do not have to worry about the nomenclature right now. Okay. So, if you look at case 1, this is case 2. In case 1, the Ex component and the Ey component have the same refractive index, which is NO, because they are both perpendicular to OA. Okay. So, as the material as the light goes through the material, the two components will still continue to be together, right, and they will move along. They will move along at a slower speed because the refractive index is not 1, right. The refractive index is larger than 1. So, the speed inside the material is lower than the speed in vacuum. We have discussed what this refractive index means, but they will go together, that is the most important thing. Okay. This is in case 1. Now, in case 2 things become a little bit more interesting. Now, you have an Ex which is along the optical axis direction, and you have an Ey which is perpendicular to the optical axis direction. So, the Ey will go at a certain speed and the Ex will go at a different speed. So, if the Ex and Ey initially were together, the Ex could start going faster, for example, than the Ey. So, one has refractive index Ne and the other experiences a refractive index No. So, they move at different speeds. Now, which one moves faster, which one moves slower, whether Ne is larger than No or the other way around does not matter for now, it is just the fact that the two of them move separately, move at different speeds. So, what this does is, if I look at the, let us say I look from this direction, now I am going to look from the y direction, just to make my drawing a little bit easier. So, then the y polarization is going to be an arrow coming out, so I will denote it by a dot, the y polarization. The x polarization will be up and down, I will denote it by a the x polarization will be up and down, I will denote it by a little line. So, this is my y polarization, this is my x polarization. Okay. So, if the optical axis is in this direction, then one of them will lag behind the other, and so you would expect that when the two waves emerge from the material, they will have a different phase, right. So, if for example, your Ex was some E0x cos of omega t plus alpha 1 and Ey is some E0y cos of omega t plus alpha 2, then there is a relative phase of alpha 1 minus alpha 2 between the two waves as they emerge, right. Now, in general, if you look at these two, for example, E0x and E0y are, you can write this down as the equation of an ellipse, right. Depending on alpha 1 and alpha 2, the relative values, the ellipse will be aligned either along the x direction, the major axis will be along x or along some direction in the xy plane, right. If let us say for example, alpha 1 was 0 and alpha 2 was pi by 2, then you can write down Ex square by E0x whole square plus Ey square will be 1, because this guy will be cos omega t, this guy will be sin omega t, and then you divide and square and add, you will get 1, right. So, this is the equation of an ellipse. Of course, for this special combination of alpha 1 alpha 2, the ellipse major axis lies along the x axis or the y axis, does not matter, depending on the relative values of E0x and E0y, and the minor axis will lie along the other one, either of x or y. Okay. In general, for any arbitrary alpha 1 alpha 2, the major axis minor axis will be rotated and be in some direction in the xy plane, but nonetheless this is the equation of an ellipse, right. So, in general, if you look along the ray, so if you look along the z direction, the electric field is going to be oscillating like this in an ellipse, okay, because that is the equation of the ellipse. just something to keep in mind, okay. And of course remember we are only talking about the electric field, there is also a corresponding magnetic field. So your actual electric field is your Ex I hat plus Ey j hat, and the magnetic field is correspondingly Bx I hat plus By j hat, and of course you always have E bar and B bar perpendicular. So you know you will have a corresponding Bx and By, right, but just keep that in mind. Okay. Now notice that the angle of incidence here is what? Is normal, right, because the direction z is perpendicular to the interface and it is also perpendicular to OA, which is the optical axis. So this is pi by 2 with respect to interface and the optical axis, okay. You can see that because this is along the z direction. Now the moment this happens there is no bending, right, we have seen that already with Snell's law, we have figured out why that happens and so on, and the same logic applies here as well. The only difference being you have different refractive indices for different polarizations, but the direction of incidence is still perpendicular and so you will not see any bending. So for all the cases we will discuss now, bending is not really going to happen. There is no refraction per se, but there is double refraction in that there are two refractive indices and we have to keep track of them, okay. So again something to keep in mind. Okay, now the next question is perhaps a little bit more natural, which is how do we control the polarization. Okay, this is important because I had mentioned at the start that there are polarizer sheets that you can use, there are circular polarizers, linear polarizers and so on, and so we have to just do a small detour to understand how polarization can be controlled. Now it is quite simple to do in principle, although in practice it is a little bit non-trivial. You can take a polymer sheet, polyethylene typically, and then you can stretch it, okay. Usually this is PE, polyethylene, and when you stretch a polymer sheet, if you have stretched plastic bags, you have probably seen this before, the polymer chains will all tend to align in the stretching direction, okay. So this is load, load, stretch. Once you have stretched it, you can coat it with a suitable coating. There are several coatings, they are called dichroic coatings. And what they will do is that they will allow the sheet to pass light without much absorbance in the polymer chain stretch direction, but they will absorb light in all the other directions, okay. So they will allow selective transmittance. So only parallel to the stretch, right. This is what you call a linear polarizer sheet. And basically linear polarizer sheet has one direction called the polarization direction, and for this case it is upward, right. So the moment you have a light source, typically light source emits light with all types of polarizations, and you pass it through a polarizer sheet that has a polarization direction like this. Initially you are going to have Ex and Ey in various ratios, right, and you have an ellipse, the electric field follows an ellipse. The moment it passes through a polarizer sheet like this, it is only going to have this polarization, the other polarization will get absorbed, okay. So this light with this single polarization is called plane polarized light. The other polarizations are absorbed. Okay, so this is how you generate plane polarized light. So here is what we are going to do. So how do we use this? So far we have sort of delved into some of these more fundamental microscopic aspects, but it is time to put this stuff to some use, right. And this will be a typical configuration. So you have this is a 3-dimensional drawing. So this is our z direction, x is up, and well, let us make x here and y here, this is easier, right. So it is going at an oblique angle, and I have a polarizer sheet, looks like this, polarization direction is like this. So the light that is coming out effectively is polarized like this, right, there is no x component, let us say, okay. And now I pass this light through a birefringent crystal. Again, we are not talking about stress optic birefringence, stress optic law and so on. I have not discussed any of that stuff yet. So the stress is not really come into the picture, the elastic part of photoelasticity has not yet been touched upon, but once you understand what goes on with a birefringent crystal, it is a simple enough thing to extend it to photoelastic materials. So the birefringent crystal, let us say the optical axis is like we discussed, it is in a plane perpendicular to z, so it is in the xy plane. So I will make the optical axis, I will denote it in red, it is in this direction. So optical axis is in the xy plane and it is in this direction at some angle. So if I take this like this, it makes an angle, let us say theta with the y axis, and it makes an angle pi by 2 plus theta with the x axis. Okay. Now what will happen is our incoming wave, so our incoming wave has Ey, let us say that is E0 cos omega t, that is our incoming wave, it is only polarized along the y direction, and Ex is 0 of course. This guy will now have one component along the optical axis and one component perpendicular to optical axis. Okay. This will go at a speed, let us say c1, and this guy will move at a speed c2 because they have two different refractive indices. And depending on how far they propagate, which means depending on the thickness of the crystal. So this is the thickness of the crystal. Depending on this, you will see a phase difference, and we can actually quantify that phase difference, right. And how do we do that? Well, the time difference, which I am going to call delta t, is h by c1 minus h by c2, right. The first wave takes h by c1 seconds to move through the crystal, and the second fellow takes h by c2, right. So the time difference between the two of them is h by c1 minus h by c2. The phase difference is simply omega times delta t, right. Remember, light passing through the crystal does not change its frequency, right, it is going at the same frequency because it is not losing any energy, we are assuming that absorbance is minimal here, and so the frequency remains unchanged. So the phase difference between the two waves is given by omega times delta t. So you can write this as omega times h by c1 minus h by c2, okay, and I will call this phase difference delta. And depending on the wavelength of the light as it was coming through the medium before it went into the crystal, the wavelength lambda and the c, the velocity of the light or speed of light in the vacuum or in the air can be related to omega by omega is equal to 2 pi c by lambda, right. That is a very straightforward relationship. So, if you put this together you will get delta is 2 pi c by lambda times h 1 by C1 minus 1 by C2, which is nothing but 2 pi h by lambda c by C1 minus c by C2. And if you recall our discussion about the refractive index, this is refractive index 1 and this is refractive index 2 because the ratio of the speeds, right, absolute refractive index. So, this is 2 pi by lambda times n1 minus n2, okay, that is the phase difference. And this is applicable for any case where the optical axis is perpendicular to the propagation direction. Okay. Any crystal of thickness h, you will always see this phase difference if the optical axis is perpendicular to the propagation direction. Okay, so let me write that down again. So, this is 2 pi h by lambda into n1 minus n2. So, now the question is, what about stress induced birefringence. So far we have sort of touched upon this, the origin of this birefringence as being structural. So, this arrangement of atoms or whatever in the material has this sort of property that the orientation is such that the response of the electrons and so on is different in one direction versus the other direction and so on. That is a structural origin for this delta, right, that is a structural origin. But there is this other thing called stress induced birefringence, and loosely speaking what happens in this case is if you have polymer, if you have a polymer or even with glass, particularly pronounced with inorganic glass, if you apply a load, then load of some sort, then the local atomic rearrangements, or in the case of polymers chain rearrangements, are such that the n1 minus n2 results from an applied stress. Okay, so, the existence of these two refractive indices comes from the applied stress. Now, naturally, since in general if you have a body and you load it with a set of forces on its boundary, the stress field varies spatially, and so the refractive index will also vary spatially. And this is a really important thing to sort of recognize. The moment the origin for the change in refractive index comes from a stress, automatically accounting for the possibility that the refractive index changes from one point here to one point here to one point here and so on. Okay, both n1 and n2 will change from point to point. So, the general way to relate the stress to these two refractive indices is via something called the stress optic law, and that basically says that if n is the unstressed refractive index of the material, then n1 minus n is C1 sigma 1 minus C2 sigma 2, and n2 minus n is C1 sigma 2 minus C2 sigma 1. I will explain what these terms are in a second. n1 and n2 of course are the two refractive indices. C1 and C2 are material constants, and sigma 1 and sigma 2 are called the principal stresses. Okay. You have probably seen, you probably had this idea of a principal stress discussed before, but just so that we are on the same page, if you take any arbitrary stress tensor like this, you can let us say it has this is a 2D problem. So, we are talking only about 2D for now, we will talk about 3D a little later. It has in general 3 independent components with respect to some coordinate system. So, let us say x is like this and y is like this. The stress tensor can be diagonalized of course, because it is symmetric, and any symmetric tensor can be diagonalized, and if it is diagonalized it is brought into this form, and these sigma 1 and sigma 2 are the principal stresses. Okay. And the direction in which this diagonalization happens, basically the orientation along which the stress tensor becomes like this, these are called the principal directions, right. So, the values of the principal stresses go into the stress optic law. Okay. Now, it is a very simple matter to obtain the difference n1 minus n2 from here. You just subtract these two equations, you will get C1 plus C2 times sigma 1 minus sigma 2, okay, from this. So, now we can go back and write our expression for the phase difference, and that becomes proportional to the difference between the principal stresses. Okay. So, this is called the principal stress difference, it is not particularly deep terminology, but okay, whatever. And so, our phase difference between the two waves is related to the difference of the principal stresses. Okay. We will combine this C1 plus C2. Remember, C1 and C2 are constants, they are not the same C1 C2 we use for the wave speed. So, I will probably make it curly like this, and we will call this C1 plus C2 as this C, right. This has nothing to do with the wave speed, it is just a material constant. Okay. So, this is really the first main relationship that we have in photoelasticity, which relates the phase change of the two waves, the interaction between them, to the sample thickness, the wavelength, and the principal stresses, the difference in the principal stresses. Okay. There is some other nomenclature you will see sometimes, delta pi 2 pi is usually denoted as n, it is called the fringe order. So, if you see that term, this is what it means. We will discuss what this means subsequently, but right now it is delta by 2 pi. Okay. So, n is h c by lambda sigma 1 minus sigma 2, and you can imagine n changes with h and changes with c. Of course, for a given material c is constant, for a given thickness h is constant. So, n really changes with this and with this, really that is what we are interested in. Okay. Alright. So, the next question that we want to get to is what types of fringes can occur. Okay. So, let us say you have a body like this, it is 2 dimensional. For now we will make our life simple and make it 2 dimensional. So, it looks like this, and then it is loaded 2 dimensionally, right. So, it is a plane stress problem for now. So, we will assume that it is plane stress, and as a result of this at every point. So, let us give some directions here. So, this is x, this is y. So, z is out of the plane of the body, right. The body is prismatic like I have shown here. So at every point the stress tensor is a function of x comma y, it is not a function of z because again plane stress, and this means that the principal stresses at every point are varying, right, which means sigma 1 minus sigma 2 is also varying from point to point, which means delta is also varying from point to point. Okay. So, everywhere in the material depending on the loading you will see a different value for the phase change despite the fact that h and lambda are the same. Remember we are not changing that, right, that is a property of the body, it is thick, we are assuming that it is uniform thickness h, and we are assuming that the light wavelength does not change of course. Okay. So, lambda is the same, and despite that you have this field of delta of x y, and that is really what we are measuring in some sense in photoelasticity. Okay. So, here is a sequence of things we will do, right, and I will start off with this in the next session. The first thing we will do is we will take light of a given lambda or a given set of lambdas. So, it could be a spectrum, like it could be white light, it could be yellow light, orange light, blue light, green light, does not matter. We will pass the light through a linear polarizer, then the polarized light goes through the sample, the stressed sample. Remember the sample is under loading, if the sample is not loaded then the whole question of N1 and N2 does not turn up because there are no stresses inside. So, we pass the light through the sample and then we use, so let us say if this polarizer is along the y hat direction, that is the polarization direction. Once it comes out of a sample, so sample we pass it through another polarizer, second polarizer, which is crossed with the first one, which is called a crossed polarizer, or this is sometimes called as a crossed polarizer, or in the photoelastic literature it is sometimes called an analyzer. We will usually call it A, this fellow we will usually call P, and then we will look at it. Okay. If there were no stresses, if there was no birefringence, even though the material is optically transparent, the first step will give you some white light, it will pass through the material, it will pass through the polarizer. The second step will give you linearly polarized light. The third step will pass that polarized light without any change through the sample, and the fourth step will completely cut it out, right, because it is perpendicular to the incident light. So, if no stresses implies no sigma, implies no sigma 1 sigma 2, implies no n1 n2, then step 5 will give you a black field, okay, or a dark field, you will not see anything because A and P are perpendicular to each other. Okay. So, what we will do in the next session is we will start with this sequence of steps, 5 steps, and then we will go one by one through each of them, and then we will see if stresses were present what they should manifest themselves at, and we will see that there are 2 types of fringes that result from the interaction of the light with this sample that contains sigma 1 sigma 2, they are called isochromatics and isoclinics, and we will try to understand how to break down their behavior, properties and so on. So, we will continue with that from the next session.